So if I have two vectors, I'm going to write them in component form. So ux, uy, uz, and I'm doing a three-component vector, but everything we do will also apply if we're just working in 2 dimensions as well. So we're going to define sort of a way to multiply vectors. So the dot product is what it's called. So dot product of u and v, and we're going to denote it u and then dot, real creative name, v, so u dot v is equal to, and now what we do is the result is not going to be a vector, it's actually going to be a scalar. What we're going to do is we're going to take each of the components, the x components, and multiply them together. So ux times vx, just multiply those numbers together, and then plus take the y components and multiply them together, and then plus take the z components and multiply them together, just like that. And so I'm just going to state a few properties. These are all really easy to verify, but they sort of will mirror properties of multiplication with numbers that we know. So first of all, we have that the dot product will be commutative, or will have commutativity. So what I mean by that is that u dot v is the same as v dot u. So it doesn't matter which order I do it. That's convenient. And then we have the distributive property for multiplying, just like with real numbers. So what that means is that if I take u and I do the dot product with a sum of two vectors, so say v plus w, well then that's just going to be maybe exactly what you would expect it to be. I just first take the dot product with v, and then add, I take the dot product of u with w. Okay, and then finally we have this really nice property that relates the dot product to the length or magnitude of a vector. So if I take u, and instead of taking the dot product with another vector v, if I take the dot product with u itself, well, I bet if you thought about it for a second, you could tell me what the answer is. But if you look, what you get is you're just going to get the sum of the squares of all the components. So what is that? Well, that's going to be exactly the length of u, or the magnitude of u, except we're not taking the square root. So it's the length squared, like that. So we have these nice properties of the dot product. So what you're probably asking now is, what is the point of the dot product? I mean, we defined it, and it kind of has these interesting properties, but what is the point? Well, the dot product sort of implicitly gives the angle between two vectors. And so what do I mean by that? Well, there's a way to actually interpret this scalar value you get when you take the dot product of u and v. And what you get is you get the length of u times the length of v, and then times cosine of theta. And what is theta? Theta is the angle between u and v. And this angle is going to be between 0 and 180 degrees, or 0 and pi radians. Okay, and so why is this the case? Well, we can see this by using the law of cosines. So if I have this vector u, and this could be in space or in the plane, and I have this vector v, so here's the angle between them. Now notice the angle really can be, it's 0 if they're lying in the same direction, or it can be 180 if they're lying in opposite directions. And so if I look at this vector right here, what is this vector? Well, it's not too hard to see by the way we add vectors that this is u minus v. And so now I have a triangle. It's not necessarily a right triangle, but I can actually write out what the law of cosine says. So the length of this side across from the angle, so the length of, the length squared, so u minus v, this length squared, equals the length, the sum of the lengths of the other two sides, so it's sort of like the Pythagorean theorem. In fact, if theta were 90 degrees, it would be exactly the Pythagorean theorem. But we need to subtract this correction term from the law of cosines, and it's 2 times length of u times the length of v times cosine of theta. And so what happens? Well, recall that the length of u minus v squared is just the dot product. So this is just u minus v dot u minus v. Okay, and this equals length of u squared plus length of v squared minus 2 length of u times length of v times cosine of this angle. And if I expand this out, so recall that the dot product is distributive, so I can sort of FOIL this out just the way I would normally. And it's also commutative, so I can combine the middle term, so this really is going to be just FOILed out like this. So it's going to be u dot u, which is going to be length of u squared, u dot minus u dot v, and then minus v dot u, but because that's commutative, that's just minus twice u dot v, and then plus v dot v, which is the length of v squared. And then write all this down one more time. And then at this point, you can probably see what's going to happen. Lots of stuff is going to cancel. Okay, so what I'm going to do is I'm going to subtract length of u and length of v on both sides, and then divide both sides by -2, and lo and behold, what am I going to get? I'm going to get that u dot v is exactly what I claimed it was. Length of u times length of v times the cosine of the angle between them. So when you think about the dot product, just think about geometrically it's the angle between the two vectors, u and v. So now we want to talk about an application of the of the dot product, and specifically thinking about this angle between two vectors, and that's the projection of u onto v. So let me just draw a picture. I think a picture kind of illustrates exactly what's going on. So if we have this vector u, and we have this vector v, and we have the angle between them, which is theta, then what I want to imagine, this projection, is if I took a light up here and shone it down on u, then wherever the shadow would land onto v, where it makes a right angle right there, so this vector right here, so basically the part of u that lies in the direction of v, is called the projection. In the notation, I put the subscript of the vector that I'm projecting onto, and then in big, the vector that's being projected. So this is the projection of u onto v. And so how is this defined? Well, it's one of those things that you could probably figure it out if you thought about it for long enough. So what we want to do, you see that we have this right triangle. It's really nothing more than the length of u, which would be like the hypotenuse, and then times the cosine of this angle. So it's just going to be the length of u. So that's going to be the length of the projection vector. It's just going to be the length of u times cosine theta. Well, that's the length, but then what direction is it in? Well, I want to put it in the direction of v. So I put a v hat. But we can actually unpack this a little bit. Okay, so let's actually write what all of these things are. So length of u, that's easy. But now cosine of theta, we already saw that in terms of the dot product, that's u dot v divided by length of u times length of v. And then v hat is nothing but v divided by the length of v. Okay, so we can cancel some stuff here. So that will cancel with that, length of u, and we'll have u dot v divided by the length of v squared. And then we just have the vector v. So this is another way to write the projection of u onto v. So it's this is sometimes called the scalar projection, and then we just rescale v by that scalar projection. And we see that this will be in the direction of v. But its length is exactly this projection right here. We can also talk about this other vector here. This is called the orthogonal projection. So the notation is similar, ORTH for orthogonal. And then we have v u. And now what is the orthogonal projection? Well, we can actually just write this in terms of the difference of two vectors. So the orthogonal projection of u onto v is just going to be u minus the projection like that. And now what we can actually see is that the projection in the orthogonal projection will always make a right angle with each other, like this. So they're always perpendicular. And so, in fact, we actually have a special name, and it's kind of hinted by this orthogonal name. So two vectors are orthogonal. And if you don't like the word orthogonal, you can just think perpendicular. If u dot v equals 0. So in other words, what this means is that cosine theta is 0, or theta is pi over 2, or if you prefer 90 degrees. And so what I'm saying here is that the orthogonal projection is orthogonal to the projection. They make a right angle. The angle between them is 90 degrees. So let's talk about one more small little topic, and it's an application of this vector projection, and that's projection onto the coordinate axes. But first, we just want to introduce a little bit of notation that is common to use. I'm not going to use it just to be consistent, but you'll see it, and that's these unit vectors along the coordinate axes. So they're I hat, and what we mean by I hat is just 1, 0, 0. So it's a unit vector in the x direction. And then you have j hat, which is just 0, 1, 0. So it's a unit vector in the y direction. And then k hat is this unit vector in the z direction. And so, again, if we have this vector v, and it has these components, vx, vy, vz, well then we can project into the I direction, and that's just going to be vx. We project into the j direction, or along the y-axis, that's just going to give us the y component of v. And then if we project along the z-axis, we'll just get the z component of v, like that. So this is called projection onto the coordinate axes. And I just want to kind of give a chance to introduce this notation, because sometimes you'll see vectors written like this. So vx I hat plus vy j hat plus vz k hat. And that really means the same thing. I just prefer this notation over this notation. But they're really exactly the same thing. Alright, so we want to take some dot products. So here, u dot v, we're just going to take the x components and multiply them together. So 3 times negative 1 plus 6 times negative 2, and this is going to be negative 3 minus 12, which equals 15. Okay, and then down here, same thing. If we have 3 components, we're just going to have 3 terms that we're going to have to add together. So u dot v is just going to be negative 1 times 2 plus 1 times 0 plus 2 times negative 1. This is going to be negative 2 plus 0 plus negative 2, so negative 4. Alright, so we want to find the angle between these two vectors. And so we know that the cosine of the angle between them is going to equal u dot v divided by the length of u times the length of v. Okay, and so what is u dot v? It's going to be 3, so 1 times 1 plus 1 times 2 is 3. And then what about the length of u? Well, it's going to be 1 squared plus 1 squared square root, so square root of 2. And then v, we're going to have 1 squared plus 2 squared, so 5, so square root of 5. So we're going to have square root of 2 times the square root of 5. Okay, and then we just take the inverse cosine of that factor, and we get that theta is approximately equal to 18.4349 degrees. Of course, we could convert that to radians too if we wanted to. And then for b, we do the same thing. So cosine of theta is going to be u dot v divided by the length of u times the length of v. Okay, and u dot v is going to be 3 minus 2 minus 1. So this is actually going to be 0. So the dot product is 0, and we're dividing by two positive numbers. So it's going to be 0. But what does that mean? That means that the angle, well, remember that the angle has to be between 0 and 90 degrees, or 0 and pi radians. So the angle has to be 90 degrees, or that's pi over 2 radians if you prefer radians. Okay, so we want to first find the projection of u onto v. So the projection of u onto v, so remember it's u and then the subscript here is the vector you're projecting onto, is equal to, well, the dot product divided by the length of v squared, and then this factor, or the scalar multiplying the vector v. So the dot product here, it's going to be 1 minus 2, so negative 1. And then the length of v squared is just 1 squared plus 2 squared, so 5. And then v, which is negative 1, negative 2. So in other words, the projection will just be negative, actually positive 1/5, 2/5. Okay, and then what about the orthogonal projection onto v? It's not really onto v, it's onto the orthogonal direction of v. Well, that's just going to be u minus the projection onto v, which is, so negative 1 minus 1/5, that's minus 6/5. And then 1 minus 2/5 is 3/5. Okay. Now we want to verify that these vectors are orthogonal. Well, let's just take the dot product. So we have 1/5 times negative 6/5. That's going to be negative 6 over 25. And then here we're going to get positive 6 over 25. So the dot product between these two vectors, so this dot this, is 0. So they are indeed orthogonal. And let's do the same thing with these two vectors. So the projection onto v of the vector u is going to be dot product divided by, the length of v squared then multiplied by the vector v, so multiply the scalar by the vector v. Okay, so what's the dot product? It looks like 0 plus 1 plus 0, so 1. And then the length of v is 2 squared plus 1 squared, 5. The length of v squared is 5. And then 2, 1, 0. So in other words, 2/5, 1/5, 0. And then the orthogonal projection is just going to be u minus the projection which is going to be 0 minus 2/5, so negative 2/5. And then 1 minus 1/5, so that's 4/5. And then 2 minus 0 is 2. Okay, and we can see that these vectors are indeed orthogonal. If we take dot product, we get negative 4/25 plus 4/25 plus 0, which is 0. So they are indeed orthogonal. Okay, so we have a box and it's being pulled a distance of 10 meters by a rope. Here's our rope. And it's making an angle of 60 degrees with the horizontal. And the tension in the rope is a constant 45 newtons. So newtons is sometimes abbreviated just with a capital N. Okay. And so we want to find the work done on the box. Well, what we need to know is that work done on an object by a force is just you take the force vector and you take the dot product with the displacement vector. And the displacement vector is just where it is traveling. Okay, so the force vector here, well, let's put it in terms of its horizontal and vertical components, or its xy components. So we're going to have the horizontal will be 45 cosine of 60. And then the vertical will be 45 sine of 60. Okay, and so what about the displacement vector? Well, the displacement vector is going to just be, well, it's only a horizontal displacement. And it's going to be a positive 10 meters there. And then 0 in the vertical. So then when we do this force dot distance, well, we just multiply the components. But since there's no vertical component, this is just 0. So it's just going to be 450. So 45 times 10 times cosine of 60. And if you recall, cosine of 60 is 1/2. So this is 225. And the units are Newton meters, so force times the distance. And then this is what's sometimes called a joule, or denoted J. But I mean, this is in a physics class, so yeah, it's 225 is the work done, and the units are in joules, or Newton meters.